Okay, let's go back and look and see what we've done quickly one last time. And then I'm going to do one last formula here at the bottom for what's called the adjusted R squared. Let me go ahead and we'll do adjusted R squared, and then we'll run back through everything really quickly. So the R squared, again, just tells us what ratio is the explained. Some people call this the estimated sum of squares. If I look at how much of the variation I can explain over the total variation, what proportion is that? 53.5% can be explained. Another way to calculate it is 1 minus the residual sum of squares over the total, or 1 minus 17.65 over 38. Well, if we do 1 minus, and then over here we do the formula 17.65 over 38, H31 over 38, okay, equals 1 minus, this is residuals are things we can't explain, over the total variation. So this is just the variation we can't explain divided by the total variation. So this tells us that 46.4% of the variation can't be explained. 1 minus that gives us the R squared, or the proportion. If you multiply it times 100, it's a percentage of the variation in price, the dependent variable that can be explained with the model. And that's all it means. And people use it as a measure of the goodness of fit of the model, because the closer these points are to your line, the smaller the residuals will be, and the higher the R squared will be. The more the ups and downs and y you can explain with your model. Now, this adjusted R squared doesn't make much sense if all you're doing is having one explanatory variable. Let's calculate it anyway, and then I'll tell you what you do with it. Be careful when you're calculating this if you're doing it by hand. We have 1 minus, in parentheses, 1 minus R squared. 1 minus R squared is the percentage of the variation that can't be explained. We have that right here, 0.46457. That's in parentheses times n minus 1. We have 4 observations, n minus 1 is 3. N minus k minus 1. K here is always the number of explanatory variables. How many variables are we using to explain price? Here we're just using 1, so K is 1. Now in our first lecture, where we used domestic car or import and horsepower to explain the price of a car, we had 2 variables. The price and is it a domestic car? But actually, now that I think about this, I'm wrong. Actually, we had 3 variables. We had domestic car for the intercept, and we had a domestic car that changed the slope, and we had horsepower. So we actually had 3 coefficients, B1, B2, and B3, that we estimated there. But here, K is just one explanatory variable. What's going on the bottom here is its number of observations minus number of slopes minus the y-intercept, really. So adjusted R squared is going to be 1 minus R squared. All right, let me do this as a formula. Equals 1 minus R squared, which is 0.53543. And then that is all times just the second 1 minus R squared, all times n minus 1, which is 3, divided by 4 minus 1 minus 1, 2. So 3 over 2. Now this adjusted R squared by itself means absolutely nothing. I can't say this enough. If all I'm doing is looking at this number, 0.30315, it tells me nothing. Nothing. What's the point? The only point behind calculating an adjusted R squared is that it is one tool, one of many tools, one of many methods that people use to ask, should I add another explanatory variable? Should I add one more? For example, if instead of just quantity explaining price, should we add people's incomes who might be buying this product? Maybe that affects the price. People's incomes go up, maybe the price will go up, right? If we had data on incomes for each point, and we wanted to throw in that second explanatory variable, we would come up with a new line with another slope for the new variable. And we'd come up with new residuals based on the new model. And we'd come up with new residual sum of squares. Now what's going to happen when you add another variable is you'll always be able to predict a little better. Adding another variable, more data, better predictions. And so adding another variable will always, almost always, to my mathematician friends out there, always in practical terms, reduce the residual sum of squares. So that's always going to increase 1 minus RSS over TSS here. It's always going to reduce the amount you can't explain, improve the amount you can explain. Since we know that R squared will always go up when you add another variable, the adjusted R squared was invented to penalize the fact that you added another variable. Suppose for the sake of argument we add another variable and R squared stays the same. 1 minus R squared is going to stay the same. 1 minus R, all that's going to stay the same. But look what happens over here on the right hand side. We're going to have n minus 1, 3, n minus 2 for k minus 1. What would happen to the R squared if everything else in this formula stayed the same? Let me paste it down here and edit it. 1 minus R squared the same. N minus 1 is still 3, 4 minus 1, but this is going to change into 1. If you add a variable and your R squared doesn't go up, your R squared will go down. It goes down a lot in this case, and it's actually negative in this case. What that would tell you is adding that explanatory variable didn't help you very much. And this is one tool, not the only tool that we use to decide should you add another explanatory variable. Couple last comments. Just to recap here, I drew the blue line, which I thought looked good. We used these formulas to calculate the best line that minimizes the sum of the squared residuals, which is the orange line. And we saw that instead of my residual sum of squares being 50, the best line reduced the residual sum of squares to 17. Then we calculated the standard error of the regression, which is one way to measure what's a common size of my residual, common prediction error, common distance between the actual and the predictions of this model. Then we calculated the total sum of squares, which is just the variance of y, but we don't divide it by n minus 1. It just gives us a way to measure the total ups and downs in y, total variation of y. And then there's this relationship that the residual, which is the variation we can't explain, the ups and downs we can't explain, the estimated or explained sum of squares, that's the amount of the ups and downs we can explain, all add up to the total sum of squares, the total variation in y. And the most common measure for fit, how good does your equation predict, how well does your line fit the data, is R squared, which is the ratio of how much we can explain of the ups and downs in y to the total ups and downs. And that's 0.535. And all that means is that, multiply that times 100, 53.5% of the variation in price, our dependent variable, can be explained with our model. On the other hand, the converse, 46.5%, cannot be explained. Then I introduced this adjusted R squared, which by itself means nothing. But when you add a variable, you watch to see, does the adjusted R squared go up or down? Because anytime you add a variable, R squared will go up. Sometimes it'll stay the same, but it'll usually go up. Since you know that'll go up, we penalize ourselves by adjusting for how many explanatory variables am I using in this model. Okay? Now, I'm going to have one more lecture that I'll do later on here to give you a graphical representation of what does R² mean. But I'll do that later, and that'll be pretty short and sweet.